Question 6, we have these three compounds drawn out as structural formulae, and the first thing it asks us to do is to actually draw out the structures. Easiest way to do that is going to be with skeletal formulae, although you could use displayed ones if you wanted to. So we've got CH2 double bond CH, and then we've got another carbon and the OH off there, so that's prop 2-ene-1-ol, and it asks us to do it for this one as well. So this one is the aldehyde. Remember, CHO is the way you write out aldehydes if you're using structural formulae. So again, it's the double bond there, and then we just draw that because obviously the hydrogen doesn't appear there. It doesn't ask us for this one, but just for good measure, let's just do that one as well, which obviously is going to look like this. And then it asks for the functional group that's common to both of these, and obviously the one that they've both got is the alkene group. The important thing is it says name. So if you wrote C double bond C, that's not the name, and you wouldn't get the mark for that. So you have to, when it says name, do what it says. So alkene is the right answer there. Sorry, that was part 2. And then in B, it's asking about the oxidation. So the suitable oxidizing agent, remember, is aqueous acidic potassium dichromate, not just potassium dichromate. Okay, that's the common mistake, that people don't bother mentioning the other components of the oxidizing mixture. It's got to be aqueous and it's got to have added acid, otherwise it just doesn't work. So you've got to learn that whole package. And then it introduces this story that hopefully you're now very familiar with, which is that when you oxidize a primary alcohol, which is what that is, remember the carbon with the OH has only one other carbon attached, so it's a primary alcohol. When you oxidize one of those, you can form either this or this. And the idea is this forms first, and this forms after more prolonged oxidation with excess oxidizing agent. And the way you therefore get either this or this is by controlling carefully to make sure that you restrict it to a very brief oxidation if you want this, and really go for it prolonged oxidation if you want that one. So the method for making acrylein, which is this one, remember, is distillation. Is the key word. And then you just want to explain briefly how that makes sure you stop here. And the point is that the acrylein is removed from the reaction mixture as soon as it's formed. Because remember, if you remember how the distillation works, the aldehyde boils away as soon as it's formed, and in the distillation apparatus the condenser carries it to a separate pot away from the reaction vessel, so it's removed from the oxidizing agent. Okay, so further oxidation doesn't happen. That's the principle behind that method. On the other hand, if you want to make acrylic acid, which is this one, you've got to oxidize for a long time. The oxidation of alcohol to aldehyde is relatively quick and easy. This is significantly slower, so you really do have to oxidize for a lot longer to convert it all into this. And so the method you use for that is reflux. And the idea of reflux, remember, is that you put the condenser on top of the flask. So again, any product that vaporizes will get condensed by the condenser, but this time it drips back into the reaction mixture where the oxidizing agent keeps getting another chance to have a go at it, and so eventually it will all get oxidized through to here. So this allows prolonged reaction without losing material by evaporation. That's the key principle of what reflux achieves. Okay, so that story of primary alcohol oxidation is a huge favourite with the examiners, so make sure you know those details. In part 4, it then wants an overall equation for the oxidation of the alcohol to the carboxylic acid. So make sure, first of all, that you show the structures. Some people are still, I think, being tempted when it sees the word equation to convert those into molecular formulae. You really must not do that unless it tells you to. You have to show the details of the structure, and you still have to balance the equation. Okay, that's the way organic equations work. So we're converting this into this, and the key thing is to recognise that because it's an oxidation, we don't put the detail in, we don't put the dichromate into the equation, because you can do it and you end up with a very complicated equation, and it's sort of pointless because we're really only interested in what's happening to the organic compound. The dichromate is there to do a job, but we're not particularly interested in what happens to it. So we cheat and we use the magic oxygen, which is drawn like that to represent the oxidizing agent. So that's what it means, the oxidizing agent, and we balance it into the equation as an oxygen atom. So remember that because it's the double oxidation, first to the aldehyde, then to the carboxylic acid, we need 2 moles of that for each mole of the alcohol. And if you think about what happens to those 2 oxygens, the first one doesn't get incorporated into the molecule. Okay, when you go from alcohol to aldehyde, the number of oxygens in the molecule doesn't change, but what you do is you lose 2 hydrogens from there, and they combine with your first magic oxygen to make a water. So that needs to be there in your equation to make it balance. The second oxidation does just add in the extra oxygen, so there's no extra water being obtained. So you can work it out like that, but it's a good idea to learn the equation just to make it efficient. In part C, it gives us an infrared spectrum, and it tells us that it's either this or this. Okay, it's one of the products of oxidation, and we have to decide which one it is. Now when you get questions like this, the important thing is to identify the key peaks and explain clearly what you've got, quoting the data sheet to back up what you've concluded. So the one that probably leaps out at you straight away is this, which you're going to suspect of being C double bond O, but remember, you don't just say, oh yeah, that looks about right. Let's just write that down. You check that it really does come in the right place. So if it's C double bond O, it should be 1630 to 1820 is what the data sheet says. So you just put your peak on 1820, so you put your marker on 1820 and you draw your line down, and you know it comes somewhere like that, and then you put your marker on 1630 and you know it goes somewhere like that, and you say, yeah, that neatly brackets the peak, so that fits with it being a CO peak. So we know we've got that. And then this, when you see this huge broad peak at the left hand end, which is very different from just the CHs that you normally see. CHs would be a bunch of sharp peaks like that, but not spread out like that. So when you see that big broad peak, you think that looks like a carboxylic acid, but again, check. So your data sheet says carboxylic acid OH. Remember, don't just say OH, you've got to say what kind of OH. Should be 2,500 to 3,300. Wave numbers is what your data sheet says. So again, get your marker, say right here's 2,500, draw your line and check that that's going to sort of bracket most of your peak. And then the same on this side, 3,300 is going to come sort of, you know, here somewhere. So you draw your line down and you say, yeah, that fits for a carboxylic acid OH. So that tells you it's this one. If it was the aldehyde, you would still have the C double bond O peak. So in a sense, that peak doesn't help you, but you still have to mention it, because you can't say, yes, I'm sure it's a carboxylic acid, unless you've identified both of those peaks. So that one fits. That one doesn't, because although it has the carbonyl peak, it wouldn't have the OH peak, because obviously there's no OH in an aldehyde. So that confirms it. So you have to mention both peaks, you have to quote their wave numbers and explain that that's consistent with the carboxylic acid, but not with the aldehyde. Part D then, we're moving on to mass spectrometry. So here's a mass spectrum of the same product, and it asks us first of all about the molecular ion peak. So remember, the molecular ion is when you have the whole molecule, no atoms have fallen off it, but it's lost one electron in order to become a positive ion, because mass spectrometry depends on having positive ions so that you can accelerate them in an electric field and use the velocity that's obtained by the acceleration to tell you what the mass was. So without the positive charge, mass spectrometry wouldn't work. So molecular ion, you just explain, means that it's the intact molecule minus one electron. And all the rest of the peaks are going to come from fragmentation, are going to come from bits falling off, basically. And that tells you that the molecular ion peak is going to be the peak with the biggest value of m over z, except that you have to remember that it usually has a little companion just on its shoulder with a mass 1 bigger, which results from the sort of random occurrence in some molecules of a carbon 13 in place of a carbon 12, and that adds 1 onto the mass. So we can say that the molecular ion peak is the peak that results from the intact molecule minus 1 electron, and we can explain that we find it by looking for the peak with the biggest m over z value, except for the C13 satellite. So that's going to be this peak at 72, because that is going to be the m plus 1 peak due to C13 replacing or being there instead of carbon 12 for just one of the carbons in the molecule. So that peak is the one that wants the star. And then it asks us just to use this molecular ion peak and say, well, does that fit with the conclusion we drew from the infrared, which was that that is the product we're looking at? And obviously you do that by invoking the idea that m over z for the molecular ion peak is equal to mr. That's the key relationship. Because the molecular ion hasn't lost any atoms, its mass only differs by that tiny mass of 1 electron, which you can ignore. So m over z for the molecular ion is equal to the mr. So basically you just say 72 m over z is equal to 72, and you just add up the mr for acrylic acid, and you find that indeed mr is 72 for acrylic acid, and that means that it's consistent with the conclusion from the infrared. So now in part 4 we turn our attention to these peaks with a smaller m over z than the molecular ion, these peaks down here. In most mass spec there are lots of little peaks, and we basically ignore them at this level because it's very difficult to account for them reliably, and they're unlikely to give us useful information. The ones that we focus on are the tall ones, which would be in this case this one and this one, because if they're tall it means there's a high probability that those will be formed by fragmentation, and usually that means that it can happen just by breaking one single bond in the structure somewhere. So those peaks can be quite helpful in figuring out what the structure is. So we have decided from the infrared and supported by the MR that we got from here, that this is the structure. So we've got CH2, CH, and if we draw it out fully, we've got that. Now remember, well-populated fragments are likely to come from breaking just one single bond. So that means that we're not going to break it here, because that would require a double bond to break. That's unlikely to happen. Same, we're not likely to break that one. So actually, there are only two single bonds to worry about. We're not going to care about the CH ones, because they would obviously only change the mass by one. But it could break here, and it could break here. And those are the ones that we have to think about to see if we can account for the peaks at 55 and 27. So if we break there, we can just add up what the masses on each side will be. So CH2, CH on that side, or COOH on this side, would give you an M over Z of, if these were the positive ions. Remember, it's hard to predict which one or ones will form positive ions, so we just have to consider all the possibilities. But if either of those positive ions formed, this one would have an M over Z of 45, and this one you've got 14 plus 13 is 27 for this one. So this peak is not one of the two we're concerned with, but this one is. Okay, so we can say yes, that fits with this structure because CH2, CH plus. Remember, you must put the bracket around it, put the positive charge outside to show that the thing is a positive ion when you're accounting for that peak. Okay, so that's what we think this one is. But this doesn't account for the 55 peak, so we're going to have to look at this fragmentation as well. So if we break it there, we would get either CH2, CHCO plus, or OH plus. OH plus, it just adds up to 17, so again, that's not one of the peaks we're interested in. But this one, you've got 27 plus an extra 28, which gives you 55. So that accounts for the big tall peak here. So you break off the OH here and you get that positive ion left behind. So that's what that peak is. CH2, CH, CO plus. Okay, so the two well-populated fragments easily accounted for. The little peaks, not so much, but we don't need to do that.